Welcome back to Uda Repo. Today, we're diving into a material that has completely revolutionized modern engineering and design. It's a substance that boasts being stronger than steel yet significantly lighter than aluminum, a combination of properties that once seemed like pure science fiction. You've seen it on the most exclusive hypercars, high-performance bicycles, and even cutting-edge sporting equipment. But what exactly is carbon fiber, and how is this remarkable material created? The story of carbon fiber begins not with cars, but with the quest for a better light bulb. In the late 19th century, inventors like Thomas Edison were experimenting with carbonized filaments, essentially baking materials like bamboo or cotton until they turned into pure carbon threads. These early carbon fibers were brittle and not particularly strong, but they were a crucial first step. The real breakthrough came decades later, in the late 1950s and early 1960s, driven by the intense demands of the aerospace industry. Scientists were searching for materials that could withstand extreme temperatures and offer incredible strength without adding much weight. This research led them to a new process involving a polymer called polyacrylonitrile, or PAN. The manufacturing process for modern carbon fiber is a fascinating blend of chemistry and extreme heat. It starts with a precursor material, which is most often that polymer, PAN. This precursor is spun into incredibly thin threads, far thinner than a human hair. Thousands of these delicate filaments are then bundled together to form what's known as a tow. This tow is where the magic truly begins. The fibers are pulled into a special, oxygen-free furnace and heated to incredibly high temperatures, often around 1000 degrees Celsius. This initial heating process, called stabilization, causes the polymer chains to rearrange and link up, preparing them for the next, even more intense, stage. Next comes carbonization. The fibers are moved to another furnace, this time heated to temperatures as high as 3000 degrees Celsius. This extreme heat, again in an oxygen-free environment, forces out almost all the non-carbon atoms, leaving behind long, tightly interlocked chains of pure carbon crystals. The precise alignment of these crystals is what gives carbon fiber its signature strength. But the process isn't over yet. The surface of the fibers is then treated to help them bond better with other materials, and finally, they are coated with a sizing agent to protect them during handling and weaving. What you get at the end is not a solid sheet, but rather spools of this strong, black thread. To turn it into the solid parts we recognize, these threads must be woven into fabrics, much like cotton or silk. These woven sheets come in various patterns, with the classic twill weave being the most recognizable. But this fabric is still flexible. To achieve its final, rigid form, the carbon fiber cloth is laid into a mold and infused with a resin, typically an epoxy. This composite is then placed under vacuum pressure and cured in a giant oven called an autoclave. The heat and pressure force the resin deep into the weave, binding everything together into a single, incredibly strong, and lightweight component. It's this complex, multi-stage process that answers one of the biggest questions about carbon fiber: why is it so expensive? The entire journey from precursor polymer to finished part is incredibly energy-intensive. The furnaces required to reach 3000 degrees Celsius consume vast amounts of power. Furthermore, the process is slow and requires meticulous control at every stage. Any impurities or variations in temperature can compromise the quality of the final product, leading to wasted material and significant financial loss. The raw materials themselves, particularly the high-purity PAN precursor, are also costly to produce. Add to that the skilled labor needed to design molds, carefully lay the carbon sheets, and operate the complex machinery, and the costs quickly add up. This is why, for many years, carbon fiber was a material reserved exclusively for the most demanding applications, where cost was a secondary concern to performance. Its first major home was in aerospace and military technology. The need for lighter, stronger, and more heat-resistant components in fighter jets, spy planes, and spacecraft made carbon fiber the perfect candidate. It allowed for designs that were simply not possible with traditional metals. From fuselage panels and wing components to rocket nozzles, the material proved its worth in the most extreme environments imaginable. Its transition from the skies to the streets, however, was driven by another high-stakes field: motorsport. In the world of Formula One racing, every gram of weight and every ounce of structural rigidity counts. In the early 1980s, one team introduced a car with a complete monocoque chassis made from carbon fiber composite. It was a game changer. The chassis was not only significantly lighter than its aluminum counterparts, giving the car a massive performance advantage, but it was also phenomenally strong, offering the driver unprecedented levels of safety in a crash. This success on the racetrack did not go unnoticed by manufacturers of high-end road cars. The allure of race-proven technology is a powerful marketing tool, and soon, carbon fiber began appearing on the most exclusive supercars and hypercars. Initially, its use was limited to non-structural parts like spoilers, mirror caps, and interior trim, a way to add a sporty look and justify a higher price tag. But as manufacturing techniques improved and costs slowly began to decrease, automakers started using it for more critical components. Today, it's common to find entire passenger safety cells, body panels, and even wheels on hypercars made from carbon fiber. This allows for breathtaking designs, mind-bending acceleration, and a level of structural integrity that keeps occupants safe even at incredible speeds. The benefits are clear: a lighter car is a better car in almost every way. It accelerates faster, stops quicker, and handles more nimbly because there is less mass to move around. So, is carbon fiber worth the astronomical cost? For a multi-million-dollar hypercar or a competitive racing team, the answer is an unequivocal yes. The performance gains are undeniable and essential for staying at the top of their game. For the average consumer, the answer is more complex. While you can find carbon fiber on everything from laptop cases to wallets, its use here is often purely aesthetic. It adds a premium look and feel but offers little functional advantage over less expensive materials. However, in areas like high-performance bicycles or professional sporting equipment, the weight savings and stiffness it provides can make a real, tangible difference in performance. The future of carbon fiber is focused on making it more accessible and sustainable. Researchers are exploring ways to reduce the energy consumption of the manufacturing process and develop new precursors from renewable sources. Recycling carbon fiber is another major challenge being tackled, as the strong chemical bonds that make it so durable also make it difficult to break down and reuse. From a simple baked thread in a light bulb to the backbone of modern marvels, carbon fiber's journey is a testament to human ingenuity. It is a material that continues to push the boundaries of what is possible in engineering, and as manufacturing evolves, we may one day see this space-age substance become a more common part of our everyday lives. Thanks for watching. If you found this interesting, consider subscribing to Ude Repo for more deep dives into the technology that shapes our world.